Okay, thanks everybody for coming. My name is Tiark Rompf. I'm an assistant professor at Purdue University. And if you don't know where that is, that's a little bit south of Chicago, what most people would call flyover country. So before I joined Purdue, I was actually at EPFL in Switzerland, and I was a member of the team that developed the Scala programming language. And of course, all of you know that Scala and Spark are very much linked, right? So Spark is implemented in Scala, and a large fraction of the user base is using Scala to do big data analysis in Spark. And the first time I actually learned about Spark was back in 2011 at Scala Days, where a guy named Matej, who was back then a PhD student at Berkeley, presented this cool new cluster programming framework, which was so much faster than Hadoop, right? Because, well, in Spark, you could keep all the data in memory and do iterative computations and so on without going to disk all the time to start a new map or a reduce phase. And, well, Spark started out as this collection-like library that would execute across a whole cluster. And since then, a lot of work has been done on improving Spark's performance, right? So it's no longer just a library that would run any Scala code, but really, if you look at the architecture, then inside of Spark, there's a whole relational database engine these days, right? So there's the Spark SQL project, and a core part of that is the Catalyst query optimizer. And if you write some user code using the DataFrame or DataSet APIs, then internally you will actually generate something that very much looks like a query plan that would otherwise be used in a relational database. Right? And from that, there's even a code generation stage that takes whole stages of queries and generates Java code at runtime, right? Which further improves performance. So with all these performance optimizations, one of the questions you might ask is, well, how fast is Spark in practice? Right? And well, we can run various different kinds of benchmarks, and I've picked a simple one here. So this is just a data set I downloaded from the Google Books Ngram viewer, right? So it contains all the words that occur in books that are in the Google Books database, and you can query words for the relative occurrences, how many times each word occurs in a given year, and so on and so forth, right? So this is not a super large data set, but it's, I think, about 2 gigabytes, so it's sizable to do something on your laptop with that, okay? And, well, if we want to load that up in Spark, then here's a little script I wrote, right? So we can just have to give the path of the file, and then I have to give the schema. And then I can use the DataFrame API to load this CSV file and create a temporary view from that. Right. So let's actually run this. Right. So I've already launched the Spark shell here. I'm using Scala. I could also use Python if I wanted to. Load demo.scala, right? Okay, there we go. And now I have this gbooks reference to the data, and I can run some query on this, right? So I can say gbooks.filter, and maybe I'm interested in a specific word. Let's just say attribute, okay? And of course, when I do this, nothing will happen just yet, because I've just constructed a data frame. Right? So this is essentially a query plan, and if now I want to get the actual result, then I actually have to run this, right? So I can do q.show, and it will actually execute the query, right? So here's a question for everybody in the room. So this is about a 2 gigabyte file, right? If I just say q.show, then how long will this take? What do you think? 10 seconds, 5 seconds? Okay, so let's try this. Whoop. Wow, that was super fast, right? And it's actually, this is too good to be true, because it's only showing the top 20 rows, and the string I looked for occurs at the top of the file, right? So this was a little bit cheating. So let's actually run this and get all the data. And so you said 5 seconds, 10 seconds? Well, I can do a count, but that doesn't really matter, right? So let's run this and see how long it takes. And well, it's running now, right? So there are some, obviously, there are multiple steps it needs to do, right? So there's a little progress counter, and well, we can wait a little bit, right, until we get a result. Right, so definitely more than 10 seconds. We're already over. We can wait a bit more. And so there's quite a bit of work that's going on internally, right? So the data is stored as a CSV file, so there's a parser for this CSV file, and then we have to traverse all the data, right? And internally, even though we have, there we go, so 47 seconds, right? So internally, even though there's like a query optimizer and so on, there's still a lot of inefficiency in the lower levels of the stack, right? Because even after we have optimized the query and there's some runtime code generation going on, it still has to map everything into the RDD layer, which has some inefficiencies to provision for fault tolerance and so on, right? So what we've been working on is actually an accelerated backend for Spark, which we call Flare. And the goal of Flare is to actually remove some of these inefficiencies that are in various layers of the Spark stack, right? So instead of generating Java code at runtime, we generate native code, right? So that cuts out a lot of the inefficiencies of the JVM, right? So we have a much better handle on memory management and those kind of things, right? And we don't occur any garbage collection overhead and so on. And we have a much tighter control over the internal data representation as well. And we can play some tricks that are not so easy on the JVM, going directly to the operating system to map input files into memory, right? So we don't have to go to the file system API, which would incur some data copying, but we can just map the file into memory and access it as if it were an array, okay? So 47 seconds if we run the query in plain Spark, and now let's run the same query using Flare. And the way we can do this is I can just say for any data frame or data set queue that I have, I can just say Flare of queue, and this will get me back a Flare data frame, right? So this is essentially a marker that says, okay, when I now call show on this Flare data frame, it will execute the accelerated version, right? So let's try this. Let's do time Flare of queue.show. And you can see there's an additional compilation step involved, and there we go, right? So we get back the same result in only 2.7 seconds, right? So from 47 seconds down to 2.7 seconds. So that's quite a nice improvement, I think. And of course, this was a very simple query, so we just had to parse this file and do something, but we can do something that is more interesting and look at some actual SQL statements, right? So I have queries from the standard TPCH benchmark here, right? So this is a simple one, right? So TPCH, for those of you who don't know, it's a standard analytical database benchmark. So it's kind of a decision support, a set of decision support queries, right? And they all look like this one, a little bit more complicated, but basically we're traversing tables that have line items and orders and customers and so on, and there are different kinds of joins, not in this query, but in other more complicated ones, right? And if I want to run this query, I can do spark.sql and then tpch.q6, right? And that again gives me back a data frame. And if I want to see the query plan, I can do explain, and it will tell me what the individual operators are. And like we did with the Google Books query, I can say Flare of queue, and it will get me back a Flare df, right? And if I do explain on this one, then it will actually tell me, okay, this is a Flare plan that is going to be executed internally. So let's again do a little bit of timing, right? So let's run the query in plain Spark. So just do q.show. Right? And again, you can see, well, this is taking a while, right? So this is, I think, on the same order of magnitude in terms of input size, so something like 2 gigabytes. It's using scale factor 2 of the benchmark set. And you can see, well, it's a bit faster than the other one, but it's also taking 22 seconds here. And let's do the same thing in Flare. So again, this is using Flare is fully transparent if you're working with data sets and data frames, right? So you only have to use this marker. And you can see that again here we're getting the same result, and it's much faster, right? So instead of 22 seconds, it's only 3 seconds. And I think if I run it again, then it should get down to 2.5 seconds. Right? So this is nice, but the question is, of course, well, does this scale, right? And also how is this implemented internally? So let's go back to the slide deck. If it shows up, there we go. Right? So this is where we're starting from. This is, again, the architecture of Spark as it is usual. And what we did with Flare is basically we added some side exits here, right? So in essence, we're replacing the standard RDD layer and the Java code generation, and we replace this with native code generation. And there are different levels of integration that we can use, right? So the first one is that essentially we keep the granularity of Spark's query stages, and we generate C code for each individual stage, right? And then we load it back via JNI into the running JVM that executes the rest of the Spark, right? So this is very, quite transparent in terms of integration. So essentially, it works with everything that Spark can do as well, and it gives us already some nice speedups. Right? But we can also go one step further, and this is sort of, in some senses, the more interesting use case. We can replace the entire RDD layer and executor architecture and optimize the whole data path, right? From parsing the input files to emitting the output. And this is what we call Flare level 2. And then when we also want to support more heterogeneous workloads that are like user-defined functions or machine learning kernels that are not as easily representable as plain data frames, then we can also hook into other more powerful compilation frameworks that provide other front-end domain-specific languages specific for machine learning or graph processing and these kind of things, right? But sort of for the results I want to show you, I'm focusing on the middle layer, which we call Flare level 2. Okay, so let's look at some more results, right? So I showed you a few very simple things in the little demo. But it's interesting to look at larger scale benchmarks, right? So we already saw one query from the TPCH benchmark, but we actually have implemented all of them. And what I'm showing here is a comparison between 4 different database systems, right? So we have Spark and our accelerator Flare, and we're comparing to a traditional database system, Postgres, and to the state-of-the-art, or one of the highly optimized state-of-the-art database systems, which is called Hyper, which is developed at TU Munich. Right? And what you can really see is that there are 2 kinds of performance levels here, right? And please note that the graph is log scale, right? So the difference you can see here, that's 1 or 2 orders of magnitude, right? And you can really see that there are slow systems, Postgres and Spark, and then there are fast systems, right? So these are Hyper and Flare, right? And if you look at the numbers, then you can see that Flare it's basically on par with Hyper, right? Which is the state-of-the-art in optimized databases. And if you compare Postgres and Spark, then even though Postgres is just a traditional database engine which does not have any code generation, and Spark actually does go to some length at runtime to generate Java code, then you can see that for many of the queries, this is not actually buying Spark all that much compared to a traditional database system, right? So there are a lot of inefficiency at various levels of the stack, really. And also note that this is a single core running time, right? So we're not looking at parallelism, we're not looking at clusters here. But this is basically just to get a baseline, right, of saying, okay, well, this is the performance we can achieve, and that we can actually get Spark to these levels of performance. Another interesting thing is that sort of when we go and optimize the whole data path, then this is something that's normally, most people will overlook this in benchmarks, right? So you would usually just report numbers, oh yeah, I have the data already loaded, and then I run some query, and then I get some nice numbers, right? But what people forget is that actually loading the data from CSV files or Apache Parquet or whatever format you have actually also takes a lot of time, and sometimes that dominates the whole query execution time, right? So on the previous slide, the benchmark numbers were all running from preloaded data in memory, and here we're looking at loading from CSV and Apache Parquet files, right? So we have optimized parsers for CSV and Parquet, and what you can see here is that obviously, if you're just running plain Spark, then Parquet is already a lot faster than CSV. But our CSV implementation is actually faster than plain Spark Parquet on, I think, all queries except one, right? And if we use our optimized Parquet parser, then we get additional speedups. And sort of in the peak, our Parquet implementation is, I think, well, almost 1,000 times faster than Apache Spark on CSV, which is the slowest one, right? So you can see that, well, there's 3 orders of magnitude in difference that you can get by really heavily optimizing all the data path. So again, this was all like single core to get a baseline, right? And then obviously the interesting question is, well, what can we do once we go parallel? And there are some very interesting aspects to observe. In particular, when we look at speedup numbers or scaling versus actual running time, right? So if we look at the graph on the right, this is scaling for Spark, right? And the purple line, that is again query 6. And you can see that, well, there's a very nice scaling behavior, right? So for 32 cores, we still get a speedup of like, I don't know, what's that, 16, 18 or something, right? So not exactly linear, but still very good. Versus if we look at Flare, then for the same query, we get scaling up to 16 cores, and then for 32, it drops again. Right? So does anybody have an idea what might be going on here? NUMA machine, yes, that's spot on, exactly. Right? So if you look at big server class machines these days, right, that have more than a handful of cores, then they will actually have multiple CPU sockets. Right? So the machine looks like this, and each CPU socket has its own locally attached memory. Right? And sort of if you look at the machine as a whole, then you have non-uniform memory access characteristics. Right? So if you're running on a core on one CPU socket and you need to access data that is stored in the memory that's attached to a different CPU socket, then you have to go across the bus and you pay extra in terms of memory access time, right? So what you need to do is you need to optimize your program so that most of the memory accesses are in fact local, right? And this is something that has not been done in the benchmark I showed you here, right? But if we enable this, then we actually get much better scaling for Flare as well, right? To the point where for query 6, when we scale up to 72 cores across 4 CPU sockets, we get a speed up of 58, right? Which is pretty good, I think. Right? And also, what you can observe is that if we're running only on 2 CPU sockets, then it depends how we allocate the different cores, right? And in that case, this benchmark becomes memory bound, so it pays off to actually split the threads across 2 CPU sockets, even though you would not have to, right? So if we have 18 cores per socket and we want to run with 18 threads, then it makes sense to run 9 threads on 2 CPU sockets each, because then we can maximize the aggregate memory bandwidth that's available to us. Okay? So these are all the kind of tricks you can play when you really embrace code generation and mechanical sympathy and trying to optimize for the individual architecture that you're running on. And just going back to the initial slide I wanted to show you, right? Even though you could make an argument, well, just add more threads and add more nodes in a cluster. If you look at the actual absolute running times, then you can see that even though sort of you get some scaling for many queries, it plateaus, right? Or it goes back up again, right? Even for Spark, right? So there are many workloads for which just adding more cluster resources does not really help, right? If you're using joins and other kinds of things, then there are many cases where you will never match the performance of an optimized C program that's just running on a single box with lots of memory. And these machines are as powerful as a smaller cluster, right? So you can buy machines with 2 terabytes of RAM very easily at Dell or rent them at Amazon, right? And this will give you much better efficiency, both in terms of like data center builds and also energy footprint, than if you're just scaling out something that runs inefficiently across many machines. Right, so these were all essentially relational workloads, sort of traditional database fare. And I just want to talk briefly about more recent work we've been doing with machine learning kernels and user-defined functions. Right. So this is essentially the FLAIR level 3 territory. Right. So we have additional APIs where we can express machine learning algorithms. So this is very similar to Spark's MLlib or other systems like TensorFlow. Right. This is just an implementation of the k-means clustering algorithm. So the details aren't super important, but sort of the takeaway is just that you can write very, very high-level code that just uses matrices and operations like computing distances and so on. And it's an iterative algorithm, right? So there's this until converged loop here, right? So it's not just executing one query, but it's really executing this computation in a loop until the assignment of clusters here has stabilized. And this is something we can also accelerate using additional compiler pipelines, right? And again, we can compare sort of what is the performance when we scale this up on NUMA machines, and compared to a normal Spark UDF implementation, which basically doesn't scale at all. We get for many of these things, we get pretty good speedups up to 48 cores, right? So k-means we get something like almost linear speedup when we enable certain NUMA optimizations like thread pinning and NUMA-aware data layout and so on. We can also run this on GPUs, and if I have a cluster with where each node has multiple GPUs, then we can also leverage all the GPUs in the cluster. And you can see that again, we can see something like a speedup of, well, about 7x or 8x across these things in comparison to a baseline Spark implementation. And more recently, we've been extending this towards actually using kernels that are implemented in TensorFlow. So we're calling this TensorFlair. And basically what you can do is you can combine relational processing using Spark with UDFs or machine learning kernels that are written in TensorFlow, right? And TensorFlow, they have their own just-in-time compilation framework, which is able to generate native code again. And we're also generating native code, so it becomes very easy to link these things together, right? So, and then basically we can generate this kernel from TensorFlow, and in a Spark query we can say, okay, select everything and group it by the nearest cluster and so on. And that's all I had in terms of technical things. So if you want to know more, then we have some information on the web. And so we also have a private beta program. Some of you might be interested in if you really want to try out FLAIR and see if it's applicable to your use cases. Thank you very much.
All right, any questions?
Is Flare open source software?
No, it's not open source, but we have this private beta program where we're working with selected companies to study use cases and so on.
Okay.
Is it available also on PySpark, or is it just on Scala?
Yes, so we don't care about the front end, right? So we're just taking query plans from Catalyst, so you can use it from PySpark, you can use it from Jupyter notebooks, and so on.
Okay, and what version of Spark is it available on?
So 2.0 and up. So 2.0, 2.1, 2.2.
That was really impressive work. So I have two questions. One is, does Flare operate on the physical plan generated from Catalyst? And like, does it do further logical or physical plan level optimization before it does cogen, or is it mainly focused on the cogen part?
So it's mainly focused on the cogen part, but we do certain things like replace. In many cases, we will replace sort merge joins by hash joins, for example, right? Because we have some knowledge about these things. But in general, I mean, we're not building a query optimizer, right? So there's other very exciting work going on for cost-based query optimization and so on. And basically, we're piggybacking on all of those things. Yeah.
Okay, thanks. So the second question is, were there any relationships or considerations of implementing Flare this way as opposed to using some of, let's say, truffle raw infrastructure like the ones used in FastR, those kind of stuff?
That's a bit of an open-ended question. So, I mean, we considered it, but then again, I think our approach is much simpler because if you look at Graal and Truffle, what those systems are really geared for is implementation of dynamic languages, right? So there's a big emphasis on speculating based on types and doing runtime profiling and then recompiling stuff as things change. And this is not really something that occurs with these database workloads, right? So we know all the types, we can just specialize on the information we have and use statistics that are already available to the query optimizer, right? So we're just like generating code and are quite happy with that, right? Also, I think we have the benefit of running outside of the JVM potentially, right? So even though Graal and Truffle, they will generate machine code, they are still sort of bound to the JVM ecosystem, right? And we don't have these constraints, right? So we can do anything that's possible on the C level.
So the query plan that you're doing the code generation from is in Scala?
That's right.
And the code generation, are you using LLVM or your own code generator?
No, we have our own code generator. So we generate C code, and then we're using Clang or GCC essentially as a just-in-time compiler. We could also go directly to LLVM if sort of compilation time is really the issue you want to optimize for.
So your speedups seem really significant. What do you think were the leading factors for why Spark was so much slower?
It's a combination of different factors, right? So one thing is that even basic operations like CSV file parsing is just not optimized in Spark, right? So the CSV parser has a lot of generality, right? So you want to abstract over what's the delimiter, what is the encoding, and so on, right? But if you specialize a parser using the configuration options, then you just remove a lot of these dispatch overhead that would otherwise need to be done for basically every character that you read, right? So that's one thing. The other thing is that just the basic scans in Spark are not very efficient when you're going from in-memory data, right? So even though there's code generation for different pieces of a query, all these different pieces need to communicate with each other, right? And we're removing these bottlenecks because we're generating code for a whole query at a time, right? And then there are things about individual operator implementations, right? So we have very, very highly optimized hash table implementations and so on, right? And all these things just add up.
All right, looks like we've got time for about one more question, I think up here. And then there is also time to ask the speaker questions afterwards.
I think earlier I saw your comparison, performance comparison with Hyper. So Flare's performance is probably at same level or a little bit better than Hyper. Then can you compare the technology used between Flare and the Hyper?
Yeah. So I think we're faster on some queries and Hyper is faster on other queries. So I think the performance we get is pretty much on par. In terms of implementation, much of the underlying ideas are the same, right? So Hyper generates LLVM code and we go through source code, so that's one difference. But then I think in the implementation, there are a lot of differences which I did not have the time to go into, right? Just in terms of the compilation architecture. So if you look at Hyper, then sort of it's very, very low level, right? Sort of you have to work with virtual registers on the LLVM level and so on, right? So if you want to experiment with different, like, let's say, hash table implementations, then it becomes very hard to do, right? Because implementing each one of them takes a large effort, right? And sort of we have techniques that are based on previous research that we did in Scala, where this becomes much simpler and sort of essentially just looks like a Scala hash table implementation if you want.
All right, and I know that there are still a lot of questions, but feel free to ask those of the speaker. I just want to make sure that everybody can get to break. Thank you all very much. Let's give one more round of applause to our speaker.
Thank you.